Okay, let's get started. Hi everyone, my name is Kien. What I'd like to present to you today are the digital radiography detectors and recent advances. I'll be showing you the overview of the technological detectors and comparing them. It helps you understand more about our subject. There are 5 main parts to my presentation. Very recently it has become possible to record X-ray images without the use of conventional film screen systems. But even now, radiography using film screen technology accounts for about 65% of all diagnostic examinations. We have some problems with a film which can show 10% of films are not available when we want them, 15% of films are hard to locate or find, 25% of films are misplaced or not retrievable, 10% of films are lost. A recent study, physicians spend 2 weeks/year trying to locate or find the films they need. The cost of physician time is estimated from $60 to $80 per study. So much for problems and now. That's all I wanted to introduce about digital imaging. Digital imaging is any modality/method of imaging that creates an image that can be viewed or stored on a computer. Only recently, it has become technically possible and economically feasible to challenge film techniques for projection radiography. Direct digital radiography systems, on the other hand, use detectors that have a combined image capture and image readout capability. DDR has 5 components include vertical stand, tube, console, detector, and couch. There are different types of DR systems available depending on the type of detectors used in them: flat panel detector-based systems and charge-coupled device array-based systems. This brings us to the next part. Indirect conversion. Indirect TFT systems are composed of 3 main layers: the top scintillation layer, a middle photodiode layer, and a bottom TFT array. The top scintillation layer, or a light layer, is where the incoming incident X-ray photons are converted into light photons. A scintillation is nothing more than a burst of light, which is why this layer is called the scintillation layer. Each photon that strikes the scintillation layer creates a small burst of light energy. Unfortunately, one downfall of using a scintillation layer is that it produces light isotopically or in all directions. The isotropic nature of this layer thus acts to decrease spatial resolution, since the converted light photons are of greater size than the incoming incident X-ray photons. Basically, the scintillation layer creates a small amount of blur on each image. The scintillation layer is comprised of either the ionic compound cesium iodide or the chemical element gadolinium. Cesium iodide is preferred over gadolinium, since it can be formed into very small rods. These small cesium iodide rods are able to produce a smaller, more focused light beam, which in turn serves to increase spatial resolution. After the scintillation layer comes to the photodiode layer. The photodiode layer is comprised of a semiconducting material known as amorphous silicon. The photodiode layer works by converting the incoming light photons from the scintillation into electric charge. The electric signal or electrons produced by the photodiode layers are then transferred to the thin film transistor or TFT layer. The TFT layer is comprised of an array or matrix of very small detector elements, or DELs for short. Each DEL is comprised of a capture element or pixel detector, which is the active element within each DEL, a storage capacitor, which stores the electric charge produced by the capture element, and a thin film transistor or switch that acts to open and close the release of electric charge leaving each DEL, thus producing the digital image. The ability of each DEL to produce a high spatial resolution radiograph is designated by the percentage of the active pixel area within each DEL. The percentage of DEL to active pixel is known as the fill factor. There is a direct relationship between the fill factor and spatial resolution in that as the active area increases, that is, takes up a greater percentage of space within the DEL, spatial resolution increases. The small overall design, which allows integration into existing Bucky tables or thorax stands. Image generation with flat panel detectors is almost a real-time process, with a time lapse between exposure and image display of fewer than 10 seconds. Consequently, these systems are highly productive, and more patients can be examined in the same amount of time than with other radiographic devices. The charged coupled device, or CCD system, is the other form of cassetteless digital radiography. CCD systems differ from the TFT systems in that, with the CCD system, there is no photocathode or TFT layer. The scintillation layer within CCD systems are optically coupled to each CCD sensor chip by either lenses or fiber optics. The CCDs are able to convert light photons into electrical signals as well as send the electrical signals to the computer for processing. Now, have two technologies in CCD, lens-coupled CCD. An array consisting of several CCD chips forms a detector area similar to that of a flat panel detector. Optical lenses are needed to reduce the area of the projected light to fit the CCD array, which subsequently converts the light energy into electrical charges. One drawback of the lens system is a decrease in the number of photons reaching the CCD, resulting in a lower signal-to-noise ratio and relatively low quantum efficiency. About slot scan CCD. Slot scan CCD systems make use of a special X-ray tube with a collimated fan-shaped beam, which is linked to a simultaneously moving CCD detector array having a matching detector width. The combination of a small, collimated beam and a concordant detector reduces the impact of scattered radiation in the image since much of this radiation will escape without detection. We have some advantages and limitations of CCD generally. Let's now take a look at direct conversion. It requires a photoconductor to convert X-ray photons into electrical charges by setting electrons free. The typical photoconductor materials include amorphous selenium, lead iodide, lead oxide, thallium bromide, and gadolinium compounds. The most commonly used element is selenium. Selenium-based direct conversion DR systems are equipped with either a selenium drum or a flat panel detector. With selenium drum, a rotating selenium-dotted drum, which has a positive electrical surface charge, is exposed to X-rays. During exposure, a charge pattern proportional to that of the incident X-rays is generated on the drum surface and is recorded during rotation by an analog-to-digital converter. Several clinical studies have confirmed that selenium drum detectors provide good image quality that is superior to that provided by screen film or CR systems. However, because of their mechanical design, selenium drum detectors are dedicated thorax stand systems with no mobility at all. And a newer generation of direct conversion DR systems make use of selenium-based flat panel detectors. These detectors make use of a layer of selenium with a corresponding underlying array of thin film transistors. The principle of converting X-rays into electrical charges is similar to that with the selenium drum, except that the charge pattern is recorded by the TFT array, which accumulates and stores the energy of the electrons. Greater clinical usefulness, since the detectors can be mounted on thorax stands and Bucky tables. Another promising clinical application of selenium-based flat panel detectors is in the field of mammography. Studies indicate that the image quality provided by selenium-based flat panel detectors is equivalent to that provided by other flat panel detectors and selenium drum detectors. In the summary, we have some key features with two types of detectors in digital radiography. An artifact is a structure or an appearance that is not normally present on the radiograph. Detector image lag and ghosting. The rapid acquisition of images can result in a latent signal from one exposure lingering into the readout of subsequent exposures. Flawed gain calibration. Gain calibration is used to compensate for sensitivity variations across the detector. Changes in the imaging geometry, beam energy, or image field between calibration and image acquisition can result in image artifacts. Detector lag and backscatter. These artifacts can have significant clinical consequences by creating ambiguous or mistaken laterality markers. Now, some newer innovations and technological advances. Tomosynthesis. Multiple low-dose exposures are given from various angles while the X-ray tube moves in an arc and the detector remains stationary. It emphasizes the contrast in a particular layer of a region of the body. Dual-energy imaging. By using a high and low kilovoltage technique, two datasets are created. Soft tissues and bones can be separately depicted by this method. Computer-aided diagnosis software programs. These are important in the early detection of cancer of the lung and breast. The suspicious areas are marked by the software for review by the radiologist. The efficiency of CAD software programs is related to their sensitivity and specificity profile. We have the advantages and disadvantages of DR here. I'd like to summarize what I've said so far in the comparison table. In conclusion, DR becoming the industry leader in radiographic imaging. DR images are displayed and stored in about 8 seconds. Drive has faster throughput, high cost of a DR system is justified only when the workload is much beyond this level. These are the materials that are cited in my presentation. Thank you for watching. Thanks for the instructions of the DR Nguyen Tai Ha.